Yeah. So good. Sure, sure, yeah. So let me confirm my slides are visible to all of you. Just a second. Just a second. Yeah. Good afternoon to all of you. Am I audible? And my slides are also visible to all. Okay, fine. So let me quickly thank all the faculty members who are sitting for the presentation over here. Brief introduction about I am a faculty at Center for Advanced Computational Research, which is being recently established in 2021. So we, along with the 15 faculty members, along and 18 project students, are working on 9 projects, uh, wherein we go with the in-depth spectroscopic studies of novel material and the applications we enlist like OLEDs, photovoltaic, and so on. So, two workstation we have for carrying out the research activities. Proudly, we can say that we are the first one to introduce the hands-on training program on DFT calculations, wherein we teach participants from all across the abroad how to carry out the DFT modeling on various type of material. So I could see that we have also arranged some expert lectures in our institution via online mode, and I could see that one of the speaker is already sitting in the room, Professor TP Radhakrishnan sir. He delivered a talk in 2021, if I'm not wrong, at our center. So we have carried out three type of. We basically go with the three type of training: computer aided drug designing, DFT modeling of material, and then detailed analysis. To the best of my knowledge, I think we have trained more than 6,000 participants from all across the world, 34 countries, including US, UK, and then up to the Canada. Got ISO certification as well in 2022. So these are some of the milestones we achieved after completing the degree from MAM's lab. So quickly, I'll move on to giving a limited time. I'll quickly move on to my topic which I have to present. The topic is unraveling the unusual phenomena in molecular aggregates. So I'll be basically presenting two of the research article which I published when I was a research scholar at MAMLAM. So this is the first new class of nitroaniline dimer. In this article, I'll highlight the unconventional type of molecular aggregate we observed for paranitroanilinic dimers. And in the second article, I'll enlist about the non-emissive behavior of J aggregate, the molecular system which we took, it was a Rubrene. So I'll go into the complete details of that. Along with these two articles, this article was also published under MAM supervision, wherein we have controlled the molecular orientation of carbon nanosheets, carbon nanoring on silicon surface, and carried out the infrared reflection absorption spectroscopic studies to control those orientation and study them as well. And then in 2017, in continuation with the previous work, we investigated the extent of charge transfer for the excited states using a concept of electron density hole distribution and the hole density distribution, which I'll shortly discuss. After 2017, in the continuation, we published another article on PBI based aggregate, which was functionalized using a biomolecule, valine. And then now we are working on various vistas, moving from computer-aided drug designing to the modeling of nanoparticles. Next. So before I switch over to what are the unusual behavior we observed in molecular aggregate, let me discuss about what are the usual behavior in molecular aggregates. So conventionally, the molecular aggregates, they are classified into two type, J type and the H type. So these J and the H type molecular aggregate, they are classified as per the three geometrical parameter. The first is the distance between the molecular center in the dimeric unit. The second one is the slippage angle, which is the angle between a transition dipole moment of a monomer and a intermolecular line connecting the centers. The third geometrical parameter on which the electronic behavior of these molecular aggregate depend, it is the polarization angle. A polarization angle is an angle which is subtended by the two transition dipole moment in a given dimer. So conventionally, the J dimers are widely known, wherein the packing of molecular are in a fashion head to tail. However, in case of H type of aggregates or H dimer, the arrangement of molecules are rather in a cofacial stacking. You can say top of each other. So J dimer are widely classified, wherein the slippage angle, this particular slippage angle is known to be 0 to 54.7. And in case of H aggregate, the slippage angle lies in between 54.7 to 90 degree. However, this concept of polarization angle is not being taken completely care of in the research articles. So we designed some system and understood what is the applicability of this alpha. Now, in 2015, moving forward from this J and conventional J and H type aggregate, we found another type of aggregate, called it as the oblique aggregate. Now, what are these oblique aggregate? I'll have a discussion in a minute while. So, this concept of molecular aggregation and the dependence of the electronic behavior, it was first explained by Kashas in 1965. I'll skip the theoretical part over here, but just a bit of it. In case of J dimer, we predominantly observe a bathochromic shift in the visible absorption spectrum, primarily because of some finite transition dipole moment to the lower electronic energy state. However, in case of H dimer, because of the arrangement of transition dipole moment, for the lower one, the transition dipole moment cancel out. For the higher energy excited state, the transition dipole moment rather add it up. So in case of J dimer, we basically observe the bathochromic shift with respect to the monomer. However, in case of H dimer, we observe hypsochromic shift with respect to the monomer. But in these two cases, we assume that either the polarization angle is 0 or close to 0. However, majority of the molecular system which we explored or reported in the literature, they don't carry the polarization angle of 0 degree. Like in this case of O dimer, we can see that although the slippage angle, is 90 degree, but due to a orientation with respect to the first monomer around 50 degree, there was some change in the electronic behavior. So I'll come on to the article over here. We explored how the dimerization or aggregation of nitroamine based functional molecular system take place. It's a well-known donor pi acceptor based system. There are experimental research, experimental reports, theoretical reports which explain how these molecular aggregate of nitroaniline system form. To continue with that, we took a para-nitroaniline, the simplest molecule in the nitroamine functionalities. We prepared its monomer, and then after that we studied segregation behavior. So the DFT calculation of this monomer, para-nitroanilinic monomer, it depicted that the para-nitroanilinic monomer is a planar in structure. On the one side we have the nitro group, on the another side we have the NH2 group. This is the dipole moment direction and the magnitude we have indicated over here. Now, given a shape of this para-nitroanilinic monomer, we initially thought of that it would form J-type dimer because of predominant intermolecular hydrogen bonding between the NH2 and the NO2 functionalities, two hydrogen bond between the NH2 and the NO2. We also thought of that there could be a formation of pi-pi stacking between the two phenyl rings over here, which could lead to a formation of a H dimer. There were well-established report in Chemical Society Review and JACS, which even state that para-nitroaniline can form J dimer or H dimer. However, on the another side, experimentally, a single crystal structure of para-nitroaniline, it showed J-type dimerization, but at the same time, the intermolecular hydrogen bonding, which initially we thought of that it could be a two-center two hydrogen bonding, it was rather a bifurcated hydrogen bonding. So to explore even more, we prepared the para-nitroanilinic monomers and the aggregate simply by increasing the concentration of the para-nitroaniline in a THF solvent. In THF tetrahydrofuran, para-nitroaniline is a less soluble in a nature. So after a certain concentration, we observed that there is a splitting of absorption band in the usual absorption spectrum. So now this splitting of absorption band we studied using the computational studies as well as the experimental studies. So after deconvolation, we observed that there is a predominant electronic transition at 363 nanometer for PNA monomer. Now, computationally, we predicted the same behavior for para-nitroaniline, and we observed that 359 nanometer corresponds to a homo-to-lumo electronic jump in para-nitroanilinic monomer. So these two values are in a perfect corroboration with each other. Next, we use a concept of a electron density, excited state electron density and hole density distribution graph. Now, why we have formulated this particular studies, because as we have already seen the aggregation behavior or the electronic nature of the molecule, it depend on the transition dipole moment vector. So to predict the direction of the transition dipole moment vector, we introduce the concept of electron and the hole density distribution map. Now, what are these electron density hole density distribution map? In a given molecule, we have multiple electronic transitions. Some of them can be single molecular orbital transition, while majority of the electronic transitions are multi-molecular orbital transition. Now, multi-molecular orbital transition involve various orbital in the ground state which excites to the different molecular orbital. Now in this particular case, the drift of electron density from one part to the another part cannot be purely accounted by using HOMO and the LUMO surfaces. So another concept of electron density whole distribution map and whole distribution map we have used using a software named as a multi-WFN wave function analyzer. Now in this particular EDD and the HDD map, what essentially they depict, HDD is the area from where the electron density move on the electronic transition. However, EDD is a area from to where the electron density moves. So as we can see, a given electronic transition, if we look at the HOMOs and the LUMOs, we won't be able to account for exactly from where to where electron density has moved. If we look at the EDD and the HDD map, we can certainly able to say from where to where the charge transfer would have occurred. Given a time frame, I will not enter into the theoretical part of this. How do we compute the EDD and the HDD map? Yeah. So using the concept of EDD and the HDD map, we even computed the direction of the transition dipole moment, because that was required to quantify the slippage angle and the polarization angle, and various molecules we have used to define or predict the transition dipole moment. In the case of para-nitroaniline monomer, we found that the transition dipole moment was rather in a plane consisting of both NO2 and the NH2 group. This is the tetracene, naphthopyrene, and this is the rubrene. So I'll be presenting my work on the rubrene as well. Yeah, so in case of dimers here, so we formulated a concept of transition dipole moment to account for the slippage and the polarization angle. So as we can see, in case of para-nitroaniline dimer, this angle corresponds to slippage and this corresponds to alpha value. Now what are these exact values? We'll see it in a minute while. Coming back to the computational studies of para-nitroaniline monomer. So DFT studies of para-nitroaniline monomer states that it has a pointer, just a second. Just a second, sorry. I am using, but I think the size is little small. So now is the mouse visible? The pointer visible? Yeah. So we have predicted the transition dipole moment vector for the para-nitroaniline monomer, and as it like we are defining over here, it passes through the center of the molecular axis. Now this transition dipole moment vector we use to account for the slippage and the polarization angle. To continue with the studies, we predicted, analyzed the experimental spectrum of para-nitroaniline aggregate, and as like we have said that there was a splitting in the absorption band. Now on deconvolation, we found that with respect to the monomer absorption band was around 363 nanometer. There was a both hypsochromic shift as well as the bathochromic shift. So initially we thought of that this could be because of multiple type aggregation, both J and the H type aggregation. But on analysis, we found that it is a single type of aggregation. We carried out some emission studies and we observed that with a given solution, we are exciting the solution at 355 nanometer or 377 nanometer. There is a single emission wavelength. So that discarded the fact that we have a multi-type aggregation in a given system. Now, this is the excitonic splitting energy we have predicted using the experimental result. I'll skip that, but please note down the value. This is 3.26 10 raised to the minus 20. Using this excitonic splitting energy, basically the excitonic splitting energy is the energy difference between these two energy level which form after the splitting of monomeric excited state. So this we evaluated using an absorption band and it came out to be 3.26 10 raised to the minus 20 joule. Now this value we have used to account for what is the aggregation number in a system. So next, moving on to the computational studies, the dimeric structure of para-nitroaniline monomer, it was optimized at a DFT level using a B3LYP 6311G, it was M062X 6311G basis set. And what we have observed that as opposite to the initial assumption of two center two hydrogen bond or a purely pi-pi stacking, we observed a bifurcated hydrogen bonding, wherein both the oxygen of the nitro group, it interact with the hydrogen via three center two atom bond. To predict the stability of these kind of dimer, we predicted the potential energy diagram wherein we changed the dihedral angle corresponding to two planar sheets of nitroaniline and then we changed the intermolecular distance between the N2 and the N3 unit, we found that the global minima of these nitroaniline para-nitroaniline dimer, it is present at a distance of I think it was 3.6. Yeah, it is at a 3.6, and the angle between these two units are corresponds to 10 degree. The computed stabilization energy was found to be 4.8 kilocalorie per mole, which was accounted because of the intermolecular hydrogen bonding. So as compared to the initial assumption that it could form a purely H aggregate or J aggregate, we rather came up with a different type of molecular aggregate which is not purely J or the H aggregate. Now, next to study the emission, yeah, please. Yeah, 5 minutes. Okay, I'll try to wind it up as early as possible. Next, we have modeled the excited state phenomena, excited state characteristics of these dimer to account for the shock shift observed in the given system. I'll skip that part. So, emission studies experimentally, it's indicated that even though we are exciting the sample at a lower wavelength or a higher wavelength, there is a emission at a single wavelength. Now, to account for the observed value for shock shift, we predicted the excited state equilibrium structure of both the S1 state and the S2 state. We observed that in the S1 state, there is a predominant change in the excited state structure. Now, these two dimeric monomeric unit, they are no longer in a planar sheet. Rather, the another one, it got twisted. Excitonic splitting energy. So this is the optimized structure of a molecular dimer using the optimized parameter of slippage angle and the polarization angle. The number of aggregation unit or the dimeric unit in the given aggregate was estimated to be around 18. So to conclude the first part of the discussion, the unusual behavior which we observed for the para-nitroanilinic dimer, neither it was purely J type or nor it was purely H type. It was rather another type of aggregate accounted with the O type aggregation. Now the next unusual behavior, only 5 more minutes I'll take. So the next unusual behavior which we observed, it was the unusual non-emissive behavior of the J aggregate. Generally in the literature, the J aggregates are classified as highly emissive in nature. Some report says that there are some non-emissive the emissive H aggregate, but literature, the non-emissive nature of the J aggregates were rather missing. So we were about to study the behavior of the singlet fission in a given molecular system. Singlet fission, I'll leave that process because time is little less. So there are research article which says that tetracene system, it can very well show the singlet fission, and singlet fission is a process. I'll just take a little bit time over here. A singlet fission is a process wherein a molecule excites to a S1 state. After that it decays to a T1 state, and then on de-excitation it liberates some energy photon which excite another ground state molecule. So this way we can create two different triplet state using a single photon. Now, if we can harness this energy of T1 state by using two electron hole pair, this can be useful in creating a very good photovoltaic system. Now, one phenomena I would like to explain, that if this T1 and the T1 state it recombine, it rather leads to a formation of a triplet recombination, which leads to a delayed fluorescence. So these two are delayed fluorescence and the triplet combination. We'll see in over here. Tetracene, I'll leave the literature reports. Yeah. So tetracene monomer, as we have seen, we can see that monomeric unit, it absorbs at a 5 to 26 nanometer wavelength. It aggregate, which is spherical in nature, it emits at a 531 nanometer. Now shift of a 5 nanometer, we can see that there is a very little shift in terms of absorption spectra can be accounted with the 2-phenylic ring present in a Rubrene system. Yeah. So this I'll leave. I'll directly come to the emissive characteristic of the molecule. Now, as we can see that there is a bathochromic shift for the Rubrene J aggregate, we thought of that there could be a fluorescence enhancement, but what we can visualize in the given picture, that on aggregation the fluorescence dramatically quenched. So to explore the behavior of why there is a dramatic quenching in the emission behavior, we studied, I'll leave that part. We have computationally investigated the electronic nature of the molecule, and what we found that in a given monomeric unit, the S1 state and the T1 state, they are not as per the thermodynamical condition for the singlet fission. The thermodynamical condition for the singlet fission is that the energy of the S1 state, it should be either double or greater than the energy of the T1 state, so that you will get two different triplet state. Now on aggregation, I'll leave that part. Yeah. So this is an optimized structure of Rubrene J dimer. Now why we have accounted for the J dimer? Because of this slippage angle less than 54.7. Moving toward the next state, Now, this is the important point which I would like to highlight. In the Rubrene J dimer, the computational study states that the S1 state energy is around 2.53 eV. However, the energy of the T1 state, it is 1.29. So, unlike the monomeric form, wherein the thermodynamical condition for the singlet fission is absent, in case of J dimer, there is a thermodynamical condition that a singlet fission can occur. Now, to prove that there is a singlet fission in a given Rubrene J dimer, which rather leads to a fluorescence quenching, we carried out the TCS-PCS studies. Now, in TCS-PCS studies, we found that there is a delayed fluorescence in a given spectrum. For a monomer, there was a fluorescence emission at approximately 9.8 nanosecond. However, for the dimers, the aggregation, the fluorescence was rather observed to be delayed in nature. The lifetime calculation says that the excited state lives for up to 150 nanosecond. After that, we have carried out the nanosecond transient absorption spectral studies, which prove that there is a positive absorption band at 530 nanometer, proving that there is the existence of a triplet band. So, in a conclusion, I'll conclude. So, a Rubrene monomer, it does not show any singlet fission, but however, on aggregation, it form a J dimer. On aggregation, it shows a behavior of a singlet fission supported by thermodynamical energy criteria. It leads to a formation of a triplet state which quenches its fluorescence behavior. The fluorescence quenching was accounted with the fluorescence quantum yield values as well. Yeah, I think time would be over by now. So with that, a quick conclusion. So two research articles I have highlighted over here. In the first one, we have highlighted that unconventional J and the H type aggregate can be replaced with the oblique type aggregate, which is a more generalized case. In the second article, we have highlighted that unlike observed aggregation induced emission in J aggregate, there can be a aggregation induced quenching via different multiple processes. We have observed one process, which is a singlet fission. Now, I'll thank all the participants for giving the time, and thanks to Professor Vijay for arranging the whole event, and thanks to ma'am as well, under whom I have completed all the research which I have highlighted over here. I went very little fast, but I hope it would be understandable. Yeah. Yes, sir, I'll explain that thing. Let me reshare my slide. So generally the singlet to triplet transitions, they are forbidden because of conservation of angular momentum. But this particular transition is allowed because how it had occurred, a molecule in the, okay, I'll put up like this. Actually, I skipped the singlet fission. So how the singlet fission occur? A molecule in the ground state, when it absorbs a photon, it goes to the singlet excited state. Now, on de-excitation, it emit a photon. Now, if the energy of this photon is sufficient enough, and we have a bimolecular system, like in the dimers in the aggregate, this emitted photon can be absorbed by the ground state molecule and can leads to a excitation of S0 to the T1 state. Now, because over here, if we look at the angular momentum change, it corresponds to S1 to T1 and then S0 to T1, and that's why it become allowed. Am I clear, sir? Am I clear, sir? So the thing is that generally these kind of singlet to triplet transitions, they are forbidden because of conservation of angular momentum. Now, why this particular electronic excitation occur? Because of first de-excitation from S1 to T1 leading to an emission of a photon. Now, if this photon emit by a delta L h by 2 pi 1 h by 2 pi, this also excites the molecule from here to here. Yeah. Yeah, I'll say sorry because I went little fast, but I hope I would be clear to all. I went very fast. The time was less. Same here, man. triplet recombinations, ADD and the HDD maps. And now we are continuing with the same singlet fission process. Now we are exploring these tetraene based solid state nanoparticles, nanofilms, how exactly they will behave. So I'll share one thing over here. Just a second. One more minute. One more second. I'll take. Yeah. My screen is visible, ma'am. Is my screen visible? My screen is visible, madam. Yeah, so if you recall that when we were about to publish this research article on unusual non-emissive behavior of Rubrene G aggregate, very difficult to get it published. But now if I look at the kind of research article which are citing the given article, they are the JPC letter, JAX, so AnguCam. So people are now exploring this J aggregation and singlet fission correlation. Yes. Which index? Asha, what exactly is that? Hmm. Yeah, great. Maybe, yeah, yeah, correct, sir. Maybe someday we'll see a quantitative parameter for this utility index as well. Yeah, she was there. Gayatri was there in the meeting. I saw Shankara Gayatri. She, ma'am, she is there.